Good morning, everybody. Welcome back to the wonderful world of physics. Last we met, we were taking a look at Newton's third law and refreshing our understanding of interactions from grade 11, as well as deepening our understanding of the role of interactions and how we could use that to think about forces in more complicated kinds of situations. So last class we took a look at that. Now today we want to take a look at a particularly weighty topic. That is the physics idea of weight. Now, have you ever experienced a situation where your sensation of weight seems to change? Can you think of an example of that? Examples? Especially in
water.
In water, your sensation of weight changes. Any other examples?
Well,
Andy?
The elevator starts going up before it starts to accelerate.
Yeah, in an elevator. Good. Some more examples. Lisa.
I've been to the moon last summer, and I'm like, really.
That's amazing. So on the moon, you definitely have a different sensation of weight. Joseph? On an airplane? Good, good. Yeah, I used to live on the 20th floor of an apartment building, and I'd be bringing my groceries home, get into the elevator, and you have to be really careful. Pay attention when the elevator starts moving, because if you're not paying attention, it starts going up and whoa, you're carrying these heavy bags, and all of a sudden they become way heavier. So of course I learned quickly. When I would get into the elevator, I'd press the button, and then I would lower the bags onto the ground like this. And for the other people in the elevator, I would explain to them I'm a physicist. I understand what's going on here. So, they don't have to worry about me. I'm fine. And then, once the elevator starts moving, that's not the time to stand up with your grocery bags. No. The best time to stand up with the grocery bags would be
When it's going down.
when you reach the top and, woo, they're so light. And then I walk off and I look back at those people who just don't understand physics. I feel very sad for them. So certainly, in situations of elevators, we've had that changing sensation of weight. And you mentioned a few other examples, but one of my favorite examples, the changing sensation of weight, comes from that vast physics laboratory which is located just north of the city of Toronto, called Canada's Wonderland. And what's the best example there of changing sensation of weight? Oh yeah. The drop zone. Who's been on the drop zone? Let's see the real physics students here. Alright, that's pretty good. Doing much better than my other class this morning. But if you haven't been on the drop zone, your homework for tonight.
Just go.
So, a very interesting situation in which to study the sensation of weight. And this is what we want to do today. And one of the most important things that we're going to be doing is to make clear in our mind what our physics definition of weight is, because that's different from your common everyday definition of weight. And we will also introduce a new idea called your apparent weight, which corresponds to our sensation of weight. We want to understand what these two things are and how to predict their values. These are our goals for today. So ladies and gentlemen, you'll be starting on page 51 of your physics handbook. And as you're getting going there, could one person from each group please bring up last night's homework? Make sure your name is on it. Choose your roles, adjust your seating, and get started.
You said piece of paper to one line.
Ladies and gentlemen, in part A, question number 3, I'm asking you to use your mathematical techniques based on Newton's second law in order to find the apparent weight of the object. This mathematical process is a very important skill for us, so I would like to check your work at this point. So on a big or small whiteboard, could you please write up your answer for question 3 and put it against the sides, facing away. Ladies and gentlemen, please turn over the whiteboards. Don't make any changes to them yet. Just have a seat and look around. There's a few things that I would like to discuss about the work on the whiteboards. So there's 2 reasons why I asked this particular question. One was to help you practice using Newton's second law whenever you're doing any reasoning about the size of forces. And the second purpose of this question is to get you thinking about when you should use the value 9.8. So in this situation, what can you tell me about your acceleration in the elevator?
0.
So is it appropriate to use the value 9.8 for the acceleration? So you have to be very careful when you're setting up Newton's second law. You shouldn't be saying that F net is equal to your mass times 9.8 because you are at rest. When you calculate the size of the force of gravity, there you do use a value 9.8, but it's a special version of it. It's 9.8 newtons per kilogram, otherwise known as the gravitational field strength. Now, does that value depend on the motion of the object, of you? No, that value is the same no matter how you're moving as long as you're close to the surface of the Earth. So be very, very careful about how you set up your second law in this type of problem solving. So take a moment to look around. You don't have to move, just from where you're sitting. And if you make any changes to what's on your whiteboard, use a different color, and I will come around to talk to your groups about those changes. Once you've done that, move on. Keep going. Hey guys. So I noticed you're making some changes to your whiteboard. What have you decided to change?
The meters per second acceleration. And we thought the apparent weight was an actual weight, not a force.
Good. So when we solve for the apparent weight, which quantity are we actually solving for? Which force?
Gravity.
So the force of gravity is what we will call the weight of the object. An apparent weight is something slightly different. What is it?
Supporting force.
So in this situation, which force would that be?
This?
So you have 2 forces in your force diagram. Which force is it that we want to solve for? In this case, it's the normal force, the supporting force. Okay, good, good. Now, when you're setting up the second law here, we always want to say F net is equal to mass times the acceleration. And what is the value of the acceleration?
0.
So what is the net force in this situation? Yeah, the net force must equal 0. But whenever we try to solve a problem using the second law, let's approach it with this strategy. So we write out the second law, and then we say, okay, what do we know about the net forces? Oh, we know that there's 2 forces. So we can write out an expression for the net force. And what do we know about the object's motion? Oh, acceleration is 0. So we can plug that value in. Okay? So use that as your starting point, and you don't have to do it on the whiteboard if you want. You can do it right into your into your notebooks and revise this calculation. Okay? Hey guys. Good. So you've made some improvements to your calculation. What changes did you make?
First of all, we've isolated the wrong variable. We were supposed to solve for f instead of fg. So we fixed that.
Even though they're equal. And we also added the f net equals mass of acceleration and the f net minus fg equals 0.
Good, good. So whenever you're starting force problems, you're almost always beginning with Newton's second law. Okay, and then fill in what you know. If you know something about the net forces, oh yeah, Fn minus Fg. Do you know something about the acceleration? Sure we do. Acceleration is 0. Okay, then you start working your way through the calculation. Okay? Good, good. Now, does that change your mathematical work for this situation here?
Yes.
Okay, so you might need a minute to go back and revise that. Okay? Good. So are you thinking about question 1?
Yeah.
All right, so what are your group's ideas so far?
Yes, we have to add another force in your accelerator upward in the elevator, the tension force from the cable.
Okay, do we agree?
Yes.
So let's think about the interactions in that situation. So what's our system object?
U.
U plus
So the person, you.
yeah.
All right, and at this moment in time, what objects are interacting with you, the person?
The scale and the earth. Yeah.
Scale and the earth. Do we agree on that?
Yeah.
Anything else?
That's all. The tension.
Well, the scale connected to the elevator pulling us up.
Well, is the cable a non-contact force?
So is it exerting a gravitational force on the person?
The cable?
The cable.
No. Well,
No.
yes, but or no. Like, isn't everything exerting like a small force on?
An incredibly small force. So is that an important interaction? No, it's not. So how many important interactions are there? Interesting. So what does that mean?
So that means there's the force of gravity and then the force of the normal force.
The normal force increases
Why do you think it's increasing?
because it's being pulled upwards and it's being pressed harder onto the feet.
Be careful with the words. How is the person moving?
Oh, they're accelerating on.
Accelerating upwards. And so what does that mean for the forces?
Unbalanced.
It has to change, so it has to get bigger. So we're not adding.
So do we need an additional upwards force to explain what's happening here?
No.
We just have to increase it.
That's what you feel.
Do we agree?
Yeah.
Very good. Very good.
Here you go.
Good, good. I just want to check with your group on the previous page.
Sure.
So what did you decide about the forces in this situation compared with the forces in this situation?
There's F net in the second one.
The forces are unbalanced.
Unbalanced.
So because the elevator is exerting upward, which means there has to be a net force pulling it up. Therefore, which means the normal force has to be greater than the gravity.
Do we agree? Now, Isaac had a suggestion there that a new force should be introduced because the cable of the elevator is pulling upwards. So what did you think about that?
Well, we said that there's no new interaction, so there's no new force.
There's a new, there's a force for cable, no, for elevator, but not you.
So the cable exerts a force on the...
Elevator.
But does the cable exert a force directly on you? Good. Good. Okay. Keep going.
And then swirly line.
Hey guys, how you doing?
That's right. We think we're doing decently well.
Good, good. So, are there any differences between the interaction diagrams or the force diagrams in these two situations?
The normal force is larger for the
Force diagram.
second situation.
Okay, and how did your group decide that?
Okay. So, we know that because in the question it says the elevator is accelerating upwards, which then means the person inside the elevator is also accelerating upwards. And then because of that, we know that the forces can't be balanced. That means that one of them, either Fn or Fg, must be greater. And then because the person is accelerating upwards, then Fn must be bigger than Fg.
Beautiful, beautiful. Now, what did you think about Isaac's idea, Isaac's suggestion?
We disagree because there's not another force added. It's just the magnitude of the normal force increases.
So is the cable of the elevator exerting a force directly on you, the person?
No. It's first exerting that onto the elevator, and then the elevator is exerting onto the scale, which then from the scale goes to you.
Awesome. You got it. You nailed it. Okay, good stuff, guys. How you doing? Good, good. So Chris, just make sure you take some time to revise that calculation. Okay? So we need to see Newton's second law and our expression for the net forces. Okay? Now, I want to ask your group about this second set of diagrams here. We have an interaction diagram and a force diagram. Are there any differences between the diagrams here and the ones up here? What do you think? A larger normal force? Do we agree? How do we decide that the normal force should be larger?
Because there's acceleration upward, which means the F net is not zero.
Mm-hmm.
And if it's going upward, the normal force should be greater than the force of gravity.
Okay, sounds good. Now, what did you think of Isaac's suggestion that there should be an additional upwards force? Did you agree or disagree?
Disagree.
Yeah, Chris, what did your group decide about that?
Everything else stays the same, which is that now the normal force is more than gravitational, but everything else is the same.
So, is the cable of the elevator exerting a force directly on you, the person inside? No, it's not. Good, good. So, if the forces are unbalanced, how should we? What else should we show in our force diagram there? Yeah, good, good. Okay. Yeah, so looking good. So, what are you predicting to see on the scale?
As we increase it becomes a heavier. And that means we'll increase.
As you cause it to
Accelerate upwards.
you're predicting the scale reading will
Increase.
Yeah, it increased.
Yeah.
It was true. That was true.
Now, can you start it off without using your hand?
Yeah.
So the mass is just being supported by the spring scale here.
Yeah, it did. It did move.
Yeah.
Does it remain changed for a long period of time?
No.
It's very short, isn't it? And how does that correspond to what you felt in an elevator?
Similar.
Yeah.
So you feel that changing sensation, but only for
Short period of time.
a short period of time. Good, good. How's it going? Good, good. Can we flip to the previous page? I just want to check in on how things are going here. So in this situation here, you've drawn a new interaction diagram and a force diagram. Are there any important differences between these diagrams and those?
Only a change in the magnitude of the normal force.
And the acceleration because of net force.
The forces are unbalanced, so there's an acceleration upwards.
Good, good. And what did you think about Isaac's suggestion? Is there an additional upwards force which explains this acceleration?
Because you're still interacting with the same objects as before.
The interaction
So therefore, there's only an increase in the normal force, and not an addition of another.
So does the cable of the elevator exert a force directly on you, the person inside?
No.
Good. Good. Now, in this next situation, what did you decide? How do we explain the fact that the scale reading goes back to normal?
So it's traveling at constant speed.
Constant velocity.
Therefore, the forces must be balanced, and no acceleration is present.
Good. Good. How does that correspond to your own experiences in an elevator?
Well, as you take off, you
Pretty
feel...
accurate.
Yeah, does that agree?
When you go off, you feel heavier.
You
when
feel
you
heavier.
go down or you're about to stop, you feel lighter.
How long a period of time do you feel heavier for when you're
Just
going up in
like
the elevator?
A really slight amount of time while it's accelerating,
And then
most of the trip it's just constant, so you feel normal. And then at the end, when it slows down, you feel lighter.
good. Good.
Take off.
Okay, doing great. Hello. How's your group doing? Let's take a moment to talk about this situation here. So we've noticed that when we pass the second floor, our scale reading goes back to normal. So how do we explain that observation? So we're traveling upwards and we pass the second floor.
So we reach its constant velocity. And the normal force and the gravitational force is equal in size.
Do we agree? Good, good. So you did the experiment with the spring scale, and when you first started accelerating the object upwards, what did you observe on the spring scale?
The reading increases, and after we reach constant velocity, the reading becomes constant.
Did the reading increase for a long period of time? Just a short period. So, how do these readings of the scale match up with your own experience in an elevator?
So, like, the larger the reading, the heavier you feel.
And when you're in an elevator, do you feel your weight change, your sensation of weight changing for a large interval of time? And after that, the elevator must be moving with a constant velocity. Good, good. Keep going.
Do we have to like for the notation? Do we have to write? Do you want us to write little subscripts for each thing?
Oh, okay. So these little subscripts, we call that our third law notation. And that's helpful to use when you are looking at the forces on different objects. So you have a couple different force diagrams going on. So in this situation, it's just one object, so it's not necessary.
But if there were multiple objects which then we should do that?
Then it's very helpful, because then you know which force is which.
All right,
Okay?
Either there's no gravity, or
Remember we were jumping up and down?
Jumping up and down. So what's your prediction here?
Reading will decrease.
So why are you thinking that it will decrease?
Because like the acceleration is negative, right?
Mm-hmm.
Since
It's
F
downwards.
ma, acceleration is negative. When you move the g to the other side, it becomes Fn equals to Fg minus ma, or like Fg plus ma, but the ma is negative. So it's actually the the Fn will be less than.
Okay, good, good. That's a fancy math way of describing it. Is there a simple way of describing why the reading has to be smaller? It's accelerating downwards, and that means
The downward scale itself is not
the downwards force has to be
greater than
and which force changes?
the normal force changes.
So the normal force had to become
Small.
good.
Things right here.
Hey guys. Do you have some ideas for that last situation, our strange elevator? What did you come up with?
There is no gravity. It's just gone.
And there are no other external forces.
So you're far from any
planets.
You
are in deep space somewhere.
In deep space?
Very deep space.
All right. Or
you are in free fall, where you're falling at the same rate as everything else. Like gravity's pulling. No, you're experiencing no net force. Your net force is zero, kind of. Well, yes, you're falling. No.
You're experiencing a net force, but since everything is experiencing the same net force, the movement relative to everything is all the same. So there's no actual contact between any of the objects within the whole elevator. So there are no forces between you and the scale. So therefore, the scale is zero.
Yes, Joseph.
very good. So this is a situation that many people will call weightlessness. Do you have a weight in that situation?
Yes. You have mass, but there's no apparent mass.
So you have a mass. Is there still a force of gravity acting on you?
Yes.
Is there an apparent weight?
Zero.
Good. Okay. You got it. Good stuff. Please grab your multiple choice letters. All right, folks. Here is your first question. Please think it over carefully. No discussion. Face down when you're ready. All right, eyes in front, please, and hold them up. Hold up those answers. Okay, thank you very much. So the class score is, I'd say about 75 or 80% correct. Correct answer is B. So let's talk through the process. It's moving downwards and slowing down. Velocity this way. Acceleration must be this way. So acceleration is upwards. So which force is larger, normal or gravity? Good. You got it. Okay, here's your next question. This requires a little bit more reading, so I'll give you some more time. Okay, eyes to the front, and hold them up. Thank you very much. So the class score was about 90%. Correct answer was F. If we think about the situation, if the reading is smaller than usual, which force is smaller? The normal force. Normal force is smaller force. So the net force must point. The acceleration must point. And situation B and C are examples where the acceleration is downwards. Good. This isn't a multiple choice question. So under what situations would the scale read 0? Liam? So one is when the elevator and you are accelerating at the same rate as gravity. And in that situation, what would that feel like? This is the recipe for weightlessness. In all the examples of weightlessness that human beings have experienced, this is exactly what is taking place. If it's you on the drop zone, or if it's an astronaut in the International Space Station. This explains why they feel the way they feel. Is it because there is no longer a force of gravity? No. That force of gravity is the whole reason why they're accelerating downwards at 9.8 meters per second squared, why they're in free fall. But it's this very special situation which helps to explain what weightlessness really means. Let's take a look at some examples of people in a weightless environment. So one of the most famous examples of this, the place where astronauts are trained for the weightless environment, is in the Vomit Comet, very affectionately named for its effect on human anatomy. And this plane travels up and down in a curving path, and when it curves over the top part, it is accelerating downwards at a rate of 9.8 meters per second squared. So for about 25 seconds, everybody inside that aircraft and the aircraft itself are in free fall. That's right. And so inside that aircraft you feel weightless. So let's take a look at some experiments they did in a weightless environment. A water balloon, pop the balloon. Surface tension of the water keeps the water stuck together in a blob. Very cool. And I guess they really enjoy doing this, so they do it a second time. And now, get a little bit thirsty, have a drink, or just blast it with some other water. Oh! But they're a bit slow catching. Blast it too hard and it overcomes the surface tension. Let's try catching all those bits. So, if you are in free fall, you experience this sensation of weightlessness, and some very interesting things can happen. So, ladies and gentlemen, we have about 5 minutes left. If you need to finish up the last bit of your investigation, if you're already done, you can start into that homework.